Welcome to the Explainer. In data science, we often think more is better. More data, more features. But what happens when you have so much information that the real story, the important stuff, gets totally lost in the noise? Let's dive in. Right, so imagine you're trying to bake a cake, but you have 1,000 different ingredients in front of you. Most of them are just useless. They're noise, and they make it pretty much impossible to find that perfect recipe. Well, data with too many dimensions works exactly the same way. The real signal gets buried under this mountain of junk.
And this isn't just some small headache, it's a fundamental, really big challenge in machine learning. And it actually has a name.
It's called the curse of dimensionality. It sounds dramatic, but it's a real thing. Think about it like this. A single point on a line is pretty easy to understand. Now, take that same point and put it in a space with 1,000 dimensions. All of a sudden, every other point is incredibly far away. The whole concept of closeness or a neighborhood just breaks down. And for a lot of machine learning models, that's a huge problem.
And this curse has some nasty consequences. Your models can take forever to train. They get easily tricked by random noise, that's called overfitting, and algorithms that rely on distance, like clustering, they just completely fail. So what do? We have to find a smarter way to reduce the number of dimensions we're working with.
Okay, so how do we fight back against this curse? Let's get into our first and probably the most famous technique for solving this problem. It's called Principal Component Analysis, or just PCA for short.
PCA is built on one really powerful but pretty simple idea. The most important patterns in your data are found where the data is most spread out. It's all about finding the direction of maximum variance. That's its entire goal.
So just picture a big, messy cloud of data points. What PCA does is it looks at that cloud and finds the single longest line you could possibly draw through it. That becomes your new number one feature, your principal component 1. Then it finds the next longest line that's at a perfect right angle to the first one, and so on. We just keep a few of these new axes, and boom, we can compress our data while keeping most of the important stuff.
But, and this is a huge but, here's the catch. PCA is completely blind. It has absolutely no idea if a data point is a cat or a dog. It only sees the overall shape of the data cloud. And that blindness, well, that can lead to a massive problem.
So this blindness brings us to a really serious complication. What happens when our goal isn't just to squish our data down, but to actually tell different groups apart from each other? Okay, look here. We've got two different groups of data, a blue class and a red class. As you can see, in their original 2 dimensions, they are super easy to separate. You could just draw a line right down the middle, no problem. But remember, PCA doesn't care about the red and blue labels. It just sees one big cloud. So it finds the direction with the most spread overall and just flattens everything onto that one line. And the result? It's a total mess. The 2 classes are now hopelessly jumbled together. The vital information that kept them separate is completely gone.
So this brings us to the million-dollar question, right? For classification tasks, we need a smarter way to do this. We need a method that actively tries to keep our groups as far apart as possible during the reduction.
And that, my friends, brings us to the second hero of our story today, linear discriminant analysis, or LDA.
So here is the absolute game changer. Unlike PCA, LDA is a supervised method. That means it actually looks at the labels. It knows which points are blue and which are red, and it uses that critical information to find the best possible way to reduce the dimensions for a classification job. This slide right here tells the whole story. It's a totally different philosophy. While PCA just wants to maximize the total spread of all the data combined, LDA has a very different mission. It wants to maximize the gap between the different groups. So how does LDA pull this off? It has this brilliant 2-part mission. First, it pushes the centers of each class as far away from each other as it can. And second, at the same time, it squishes the points within each class tightly together, making each group as dense and compact as possible. So, we've got these 2 powerful tools, PCA and LDA. How in the world do you know which one you should be using? Well, it really just comes down to what you're trying to do with your data. Okay, so here's your final takeaway, your rule of thumb. You should use PCA when you have a more general-purpose goal. Maybe you want to compress your data or visualize its main structure or just get rid of some noise, and you don't really care about specific labels. But if your end goal is to build a classifier that can tell different groups apart, LDA is almost always going to be the better tool to use first.
You know, when you really think about it, dimensionality reduction teaches us a powerful lesson that goes way beyond just data. The real key to understanding isn't always about collecting more and more information. Sometimes it's about skillfully identifying and removing what doesn't matter so you can finally see the true signal hidden in all that noise.